At this point, we've gone over work and energy. Now we're going on to the conservation of energy. A conserved quantity is any quantity that remains constant over time. In this example, we start with a glass window, and the glass window is shattered into a bunch of tiny glass pieces. Mass, in this case, is a quantity that's conserved because the mass of the initial window will be the same as the mass of the glass pieces, even though it takes a different form. Let's also define mechanical energy. This is the sum of all kinetic and potential energy, which includes gravitational potential energy and elastic potential energy, that is associated with an object or a system of objects. So we'll call mechanical energy ME. That's equal to kinetic energy plus the sum of all potential energy. And for now, we're going to disregard non-mechanical energy, but that might come in later chapters. So now let's look at the conservation of mechanical energy. In the absence of friction, mechanical energy is conserved. So in other words, the sum of the initial mechanical energy is equal to the quantity of the final mechanical energy over time. We'll take this situation with a roller coaster at the top of a ramp. It starts from rest at a very high height, and then as it falls towards the ground, reaching a level of 0, it has a greater speed. So if we wanted to simplify this equation a little bit more to show how energy is conserved, we know that the initial velocity is 0 because it starts from rest, so we can cross out that part. We also know that the final height is 0, so we'll get rid of this. We're left with mg times h initial equals 1/2 mv final squared. We can also cancel out the m because we see that on both sides. We get that g times the initial height of the roller coaster equals 1/2 times the final velocity squared. And if we had numbers in that problem, we could actually solve to find the final velocity. And just a small note, it's slightly more complicated in situations where the track has friction. So this is an imaginary roller coaster with no friction on the track, but if the track were to have friction, it would lose some energy to friction along the way. Let's look at a practice problem. A bird is flying at 18 meters per second over water and drops a 2-kilogram fish. If the altitude of the bird is 5.4 meters and friction is disregarded, what is the speed of the fish when it hits the water? So let's plug in our equations. We know that initially this fish has gravitational potential energy because it's high above the water. It also has some kinetic energy because the bird is carrying it at a speed of 18 meters per second. We'll plug in those two, and then we're searching for its final velocity, so kinetic energy again. Now we can cancel out the mass of the fish because it's going to stay the same the whole time. We're left with GH, so we'll call that 10 times 5.4 plus 1/2, and the initial velocity is 18 squared. That's going to be equal to 1/2 times the final velocity squared. Now we'll simplify. We get 10 times 5.4 plus 1/2 times 324 equals 1/2 v squared. We'll add these numbers together on the left side to get that 216 equals 1/2 v squared. Then simplify again to get that the final velocity is 20.7 meters per second. That's how fast the fish is moving when it hits the water. Number 2. A box is projected up a long ramp at an angle of 30 degrees with an initial speed of 8 meters per second. If the surface of the ramp is frictionless, how high up the ramp does the box slide? And then we also want to know what distance up the ramp does it slide. So we'll start by solving for height. We know that in the beginning, the box is moving at some speed, so it has kinetic energy. We know that it starts from a height of 0, so we'll call the initial gravitational energy 0. In the end, it has a height, so it has gravitational energy, but it's come to a stop, so it has no kinetic energy. Now let's plug in our numbers. 0.5, we'll cancel out the m's because those appear on both sides. So we get 1/2 times 64, that's 8 squared, equals 10 times h. That's what we're solving for. Now we see 32 equals 10h. Divide both sides by 10. And we see that the block reaches a height of 3.2 meters. We'll call that h. Now we're solving for the length up the ramp, so this distance, we'll call that x, that the box slides. So for this, we'll use some trigonometry. We have this side h is 3.2, the angle is 30 degrees, and we're solving for x. So we'll say sine 30 degrees equals opposite, which is 3.2, over hypotenuse, x. Therefore, x equals 3.2 over sine 30 degrees. We know that the sine of 30 degrees is 0.5, so we'll divide to get that x equals 6.4 meters. That's how far the box travels up the ramp. Number 3. As a 4-kilogram rock drops from the edge of a 40-meter cliff, it experiences air resistance with an average strength of 20 newtons. At what speed will the rock hit the ground? So in this case, we're going to need to use work. So we'll start in the same way. We have the gravitational potential energy minus, we'll call this work due to friction or air resistance, and that will equal the final kinetic energy, 1/2 mv squared, when it hits the ground. Now we can plug in our numbers. We know m is 4, g is 10, and h is 40, because that's how high the cliff is, minus. Now work is force times distance. So if the air resistance is doing a force of 20 newtons over a distance of 40 meters, that's how high the cliff is, we can plug in those two numbers, and then that will all equal 1/2 times 4 times the final velocity squared. Now we can simplify a little bit. We'll get 40 times 40, so 1600, minus 800 equals 2v squared. So 800 equals 2v squared. Divide both sides by 2. V equals root of 400, or V equals 20 meters per second.